Off we go. Okay, so today's lecture is about connectivity again, uh, and logarithmic space. So, okay, here's some stuff we've done in the past. Yada, yada, yada. Here's a lecture where we talked about connectivity, but we did it randomly. And since then, we've been sort of developing all these sort of analytical tools to understand random walks better. And today is supposed to be, well, one of the big payoffs for all that labor. Okay, so on the kind of technical side, I'm going to expose you guys to something called expander graphs, certain graph operations, in particular the zigzag product is pretty curious. And we're going to have to do a little bit of tensor linear algebra, just a little bit, to help us get through the proofs. So those are new. And the whole point is to be able to do this deterministic connectivity in logarithmic space. So let me remind you of some slides from before. But the basic question, I give you an undirected graph. I want to know for two vertices S and T, can S get to T, right? And what we teach in standard algorithms class is, take advantage of the space. If you just mark the vertices that you've already visited, then it's very easy to do this in linear time. But if I restrict the space, then you can't leave, these breadcrumbs everywhere. And that's what makes this problem much more challenging, much more interesting. And so we took a poll a few weeks ago for various stages of this problem in terms of space. So, of course, linear space, you guys know this, BFS and DFS. For polylogarithmic space, there's something called Savage's theorem, which you would have learned about in the complexity class. For log n space, most of you guessed yes. A few said no. I'm not sure if there's liars. But anyway, we were able to show that random walks, just randomly walking out a graph, will with high probability figure out if S can reach T. Okay. And then, what else is there to say? Okay. But that left open this question of what can you do without the randomness? Can we figure out how to do connectivity in logarithmic space deterministically? And there we had a split vote where half the class thought yes and half the class thought no. So, all right. So what was at a high level, what happened in the random walk? In the randomized one, we just analyzed random walks, and it turns out this question can be posed in terms of what is the cover time. If I started walking from S, how long does it take to visit everyone? And we can actually get a polynomial upper bound of m times n. The proof technique was kind of interesting too, because we detoured through electrical networks. Okay, but the question now is, okay, what can you do without randomization? Okay, so let me just review some basic facts that we've picked up. One, from our first lecture about random walks, is that every random walk has a stationary distribution. It's unique if it's strongly connected. That's, of course, the case for an undirected graph. Second fact, so for undirected graphs, not only does it, of course, have a stationary distribution, but that distribution is proportional to the degrees. The odds of being at a particular vertex is completely proportional to its degree. Fact 3 is that if we had, if mu1, mu2 through mu-n denote the eigenvalues of the random walk matrix, then the convergence rate to the station distribution is sort of exponential in the spectral gap. 1 minus the either mu2 or the absolute value of mu-n, whichever one is bigger. Okay, and that gives an upper bound on the convergence rate towards a stationary distribution. Okay, these also played a big role last class, so hopefully they're getting more and more familiar. Okay. All right, so an important character in today's class is something called an expander graph. So expander graph is a graph where the spectral gap is at least a constant. Okay, so these are just graphs where random walks mix and reach their stationary distribution very fast. Okay. All right, so let's see. What did I erase here? Okay. So as a warm-up question, and if you already have seen this question before, don't answer, because I know I've asked it before in some previous classes. Uh, in general, we want to figure out deterministic connectivity, but let's look at the special case of constant degree expanders. So these are graphs where random walks mix very rapidly to a stationary distribution. Okay. Can we figure out deterministic connectivity for constant degree expanders? Any ideas? Okay, I have a rhetorical question coming up, I think. Here, let me give you a more simpler question. What is the diameter of an expander, or even a constant degree expander? What is the diameter of a constant degree expander, and why? Of course, it's at most n. My question is, can we do something more aggressive? Okay, why? Well, let's try to work with just the definition I have, which is in terms of random walks. So here all I have is that the spectral gap is gamma. So we're taking just that perspective, which is different from last year. It'll come out the same. So in terms of, so all you know really is that on an expander, you can reach the stationary distribution at sort of like an exponential rate. Because let's say that the spectral gap is 1/2, right? So you're going to the stationary distribution at a rate of like 1/2 to the k for k steps. I don't know why they have a chair here. Like, I don't know if someone actually sits in this chair. Seems odd. Well, you're gonna have to articulate because roughly I said you have information A, prove B, and roughly you just said if A, then B. So there's got to be something more in the middle, right? I mean, I'm just trying to push you to articulate how to make that connection. Diameter is lower bound for, well, why? So I think you're on the right path, but let's try to articulate this. Okay. So let's say you're starting from some vertex S. So X is just puts all the probability mass on vertex S and 0 elsewhere. Okay, let's see what happens. I start randomly walking from X, right? The stationary distribution is, let's say that the constant degree is D. Okay, so the stationary distribution is like D over 2M. Okay. So, okay, what goes in this box? If the spectral gap is 1/2, all right. Yeah, I'll just be lazy and just put an n there. I guess it should be at least be square root n. Okay. All right. If I set k to be log n, so I'm taking log n steps, okay, then this becomes upper bounded by Yeah, or better yet, 1 over poly n. Okay. All right, so, all right, I claim that this should show me that, okay, so what does this represent? I start at S, and I take k steps. And I ask, what are the odds of being at a vertex V? Okay. I want to show it's greater than or equal to something based on that. I mean, more precisely, I kind of want to argue it's at least 0, but why? Okay. All right, so it has to be at least the over 2m minus something polynomially small in n, and that thing's at least 0, right? All right, so what does that tell us? That means that if you take roughly log n steps, 10 log n steps from S, you have a non-zero chance of reaching V for any V, right? Okay, so what does that say about the diameter? It's at most log n, because we could get there with non-zero probability in log n steps. All right, so if we can, that's right. So, okay, at some level, the fact that we go to a stationary distribution really fast also means we have a decent chance of getting anywhere really fast. Really fast maps to few steps. Okay. All right, so that's very nice. Okay. All right, so if now you have this fact that the diameter of a constant degree expander, or the degree didn't really matter there, is small, it's at most log n, because the spectral gap is big. Does that give any hints? If not, I have one more rhetorical question. Okay. No, it's not like Savage's theorem. That will still give you a log n overhead, I think. All right, here's another question. This one's simpler. Imagine I'm executing a random walk on a constant degree expander. So each step I need to generate some random bits to choose the next neighbor. How many bits do I need for each step? Constant. There's a constant degree thing. As opposed to like if I had degree n, you'd need log n bits or something like that, right? Okay, so, all right, the diameter of the graph is log n. So I can get from point A to point B in log n steps. And each step really only has constant number of choices and can be encoded in log n bits, or sorry, constant number of bits. Okay? All right. Those are the main two hints. Huh? Sure. What's everything? Well, okay, let's just do the question of I give you S and T, and you want to figure out if S can reach T. So you say you're already at S, right? Well, you know that it only takes log n steps to go from S to T, right? Okay, good. But how do I, okay, so we know if you randomly walk around, you might find T. Fine, that's what we did last time. But we can't do randomization. There's a short path from S to T. It doesn't have to be the fastest algorithm in the world, but the space should be small. Let me ask another question. How many bits would it take to write down that short path from S to T? Okay. So there's what? Constant number of choices here, 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 right? So at the end, you only need log n bits to go from S to T, okay? You can just enumerate it. You can guess all log n length bit strings or 10 log n length bit strings, and that takes polynomial time and log n space, right? Because it's just a counter, okay? So on a constant degree expander, you can actually just enumerate all paths from S of up to log n steps and figure out if you can reach T. Okay. All right, so, all right. Okay, so if you have an expander graph with constant degree, okay, then actually you can just enumerate everything and figure out the solution. So this is actually the easiest kind of graph. Before moving on, I mean, I think it's good for me to at least comment on something sort of interesting about expanders. On one hand, the graph mixes well, so it feels like it's very well connected, right? Random walks mix really fast. You can go anywhere really fast. It's very small diameter. On the other hand, we're asking for something with constant degree. So there's very few kind of degrees of freedom. And those seem to sort of be in opposition with each other, right? Like something like a click would have also be an expander. One step can go anywhere, but that's very high degree and wouldn't be very useful for our case. So the fact that there even exists constant degree expanders is non-trivial, and it might turn out to be a homework problem, okay? But they do exist. And so it's a very important fact that you have these graphs at some level behave like a complete graph. They, not in one step, but in just a few steps, you can get anywhere. So structurally, it behaves a lot like a complete graph, but the graph itself is very sparse. There's very few edges. Each vertex locally looks like a very small kind of sparse graph, right? Okay, so it's like a very smartly connected graph. Okay, so expander graphs. And so this has implications for many things besides random walks, but we'll mostly focus on the random walk aspect. Okay, all right, so we know how to solve the problem on these constant degree expanders. And now the rest of the class, we want to do the real theorem. We want to show that we can do any graph in logarithmic space in polynomial time. Okay, so this is a relatively recent result, right? This is less than 20 years. So I think it's one of the more exciting things in the last 20 years. Right? Any questions? Because it's just going to go downhill. So, if you want to parachute out, that's your chance. Okay. All right. So what's going to be the high level idea? It's kind of an amazing approach. All right. So you're given some input graph G, which of course is not a constant degree expander. It would be great if it was, but in general, it's not. It may have very bad mixing time. Okay. But somehow we're going to take G and we're going to sort of manipulate and adjust G. So we're going to apply graph transformations to G. So I'm going to take G, output a graph H or G2, and output a graph G3, and output a graph G4, and output a graph G5. And as we do so, we're going to A, keep the degree small, okay? And two, we're going to gradually make the spectral gap bigger and bigger. Okay, so I'm going to take G and I'm going to gradually transform it into a constant degree expander. Okay. Now, we only have logarithmic space. So I can't actually take G and rebuild an entire graph and write it down, and rebuild an entire graph and write it down, because that's, of course, taking n space. So everything's going to be kind of implicit, where like at some level, if I'm looking at G10 and I want to simulate a random walk on G10, I need to be like, oh, for this vertex, what's the 10th neighbor, right? And I need to basically answer this question implicitly. And then based on the construction, I may look at G9 and ask a similar question. It'll be something implicit. It'll be more clear when the details come. But at some level, we're not going to explicitly build the graph, but we'll pretend we'll build the graph and be able to sort of answer the information we need to actually be able to simulate a random walk on the constant degree expander. Okay, so we'll implicitly build a constant degree expander. And once we sort of have that, then we could do the de-randomized enumeration approach, and we're just done. Okay, so something magical is going to happen in the transformation. Does it make sense at a high level? Okay. Okay, so what are the two graph transformations? The first one's relatively simple. You might have seen before. It's just going to be something called graph powering. Okay. And then the second one is sort of this crazy thing called the zigzag product, and that's where we're going to spend most of our time. And it's not clear that you're going to walk out fully understanding what's going on, but that's okay. We'll hopefully prove that it works, and then it'll take some time to, I think it takes everyone some time to digest this. Okay, so, all right, so the first one, so one thing I should point out. All right, we're just going to assume that your input graph is a regular graph with some nice constant degree. Okay, so regular means everything has the same degree. This is really not such a big deal because you can do things like, okay, I'm stuck with a vertex with very high degree. How do I make the degree smaller while preserving connectivity? Okay, we'll split it up. Something like that, right? I could split it up into more if I want to. And then, we can do silly tricks if I want to make sure everyone has the same degree. Let's say they all have pretty small degree, but they're not uniform. Okay, I'll add some self loops or something to pad the degrees up, and that's fine. Okay, so, there's some pre-processing you can do to the input graph. You can probably do it implicitly. You just have to be clever about it. And it's not really the essential point of the proof. Okay, so we're going to assume everything is regular, some nice D. So the constant degree part's not the hard part. And both of our graph transformations will preserve regularity. So I'll always be talking about a constant degree graph because we start with a constant degree graph and we'll keep making more regular graphs. Okay. All right. Okay. So that's just one technical thing. All right. Powering. This one is simpler. So, okay, G squared is just going to be, I take G, I imagined a graph where each edge corresponds to 2-step walks on G. G3 corresponds to 3-step walks on G, right? So I guess for a path, I, drew out sort of the examples. So G squared, you can walk 2 steps, or you can do self loops, or, you can go there and back, which gives you a self loop. That's why G2 looks the way it looks. And then GC and so forth. Okay. So you just imagine generating edges for all k edge walks, and one technicality is that you may have many edges repeat because there may be several ways to get from point A to point B with 5 edges or something. So you'll have that many edges with multiplicity. Okay. Fine. So if you're looking at a random walk on GK, which is k steps at a time, 1 step on GK corresponds to how many steps on G? K. So RK, like literally the original R raised to the kth power, gives you the random walk matrix for this GK graph. Okay. All right. So what would the eigenvalue? Let's say that R had eigenvalues 1, mu2, mu3 down to mu(n) as usual. What would be the eigenvalues of R to the K? They'll be raised to the K. So if you remember the spectral theorem, you have this kind of orthonormal thing. To do the proof, we would go via the normalized version to get the spectral theorem, but then you would do it and then undo the normalized part. So the eigenvalues just get powered up. All right, but this is good, right? Because in general, mu2 and mu(n) should be bounded away from 1 and -1, and raising it to the kth power will bring it further away from 1 and -1. Okay. So the spectral gap gets better. Hopefully I did this right. But whatever the spectral gap of G is, it's going to be like 1 minus 1 minus gamma G. So this would be either mu2 or mu(n), right? And so it's raising mu2 to the kth power of mu(n) to the kth power. Okay. And fine, so that's good. So we're improving the spectral gap. which makes tons of sense, right? Because it's just asking like a spectral gap is really saying how fast does the random walk mix, and here I'm just saying, oh, one step on this graph is 10 steps on the original graph, so it should mix 10 times as fast. Like that's not too surprising. Okay, what is the degree of this graph? If G was regular, was degree D. So every vertex had degree D originally. What is the degree of GK? The kth power of G. Yeah, D to the K. Because each walk had D choices, D choices, D choices, D choices. Okay. So that's what we're really paying. Okay. So the improvement in the spectral gap is fantastic, but the degree goes up. And that's the issue. Okay. So, all right. So good. So at some level, we can make some progress on the spectral gap by just taking the power, but the degree goes up. And remember, we want to keep the degree small so that we can do enumeration at the end. So that's where this much more sophisticated thing is going to come in. All right, so I hid the bottom half because that's where it gets complicated. Okay, so it's going to be called the zigzag product. Okay, and it's a little bit obscure. At some level, let's say that G was originally like a degree 5 graph or something. Okay, and what we're going to do is we're going to bring in a vertex H that has 5 vertices. See if I can count to 5 correctly. Okay, some graph H that has 5 vertices. So the number of vertices in H is going to match the degree in G. Instead of 5, it might be more like 100 or something, but still. Okay. So, but H is in general much smaller than G. The number of vertices in H is not asymptotically large like N or something. Okay. All right. So the set of vertices is just going to be the product of one vertex from G and one vertex from H. Okay. Now, before I unveil the edges, I want to say, the high level goal of the zigzag product is to decrease the degree. Okay. The idea is that the graph powering step has already made progress on the spectral gap, which is great, but it's hurt the degree. And so what I want to do in this step is try to bring the degree back down, but not kill the spectral gap too much. The spectral gap will get a little bit weaker, but we're hoping that's modest so that overall we can kind of break even, where we improve the spectral gap, but the degree didn't actually end up going up between the two operations. Okay. And so the idea is going to be that at a high level, taking one step in H is actually going to tell us where to step in G. Okay. So why? The idea is that H has 5 vertices, say numbered 1 through 5. If I take a random step in H and I land on vertex 3 or something, I'm going to use that and go to G and say, go to the third neighbor of the current vertex in G. Okay, maybe we take one more step back. So in the vertex step is going to be the product. So I'll always be sitting on one vertex in G and one vertex in H. And H we're going to use to sort of control steps in G. What the algorithm is going to do is something like take a random step in H, and I'll move one here. And let's say I'm at vertex number 4 or something on the H side. And I'm going to look at my G vertex and say, go to the 4th neighbor of V, which might be like this, something like that. Okay. So at some level, we're going to use H to control the degrees of freedom in G. But a nice thing is that H has a very small degree because it's a very small graph. So there's sort of smaller degrees of freedom controlling this higher degree graph over here. Okay, so now let me try to unveil the details and see if we can make some sense of it. Okay, so I'm standing at a vertex in the product that should be VG times VH, not VE. Unfortunately, that will repeat in all the future slides. Okay, so you're at a vertex in the graph that corresponds to one vertex in G and one vertex in H, but I'm thinking of the vertices in H as indices between 1 and D. Okay, that's why I use I1. And given two indices corresponding to the degree of H, K1 and K2. So these are in principle much smaller numbers than between 1 and D. Okay. Here's what we're going to do. Okay, so we start at V1, I1. Okay. And based on K1, I'm going to go to I2. Okay. So I2 is going to be the K1th neighbor of I1. Okay. And then now, okay, I'm going to look at I2 and use that and go from V1 to the I2th neighbor of V1, which is V2. So I take a step in H, look at where I am in H, and use that to take a step in G. Okay. And then this part is sort of exotic. So V1 goes to V2 because it was the I2th neighbor or something. But on the flip side, V1 is some I3th neighbor of V2. Okay. So we're going to use that to go from I2 to I3. Okay, so you're going to look backwards and say, okay, V2 was the I3th neighbor of V1, and I'll use that to update my I2 to I3. Okay, that feels a little bit technical. I'll explain the idea in a moment. And then lastly, I still have this other index K2 that I haven't used. Okay, and that's going to be used to update from I3 to I4. Okay, all right, so the high level idea is to take a step in H, which is a lower degree graph. So you're choosing smaller degrees of freedom. Take a step in H and use that to take a step in G. To use where you land in H to take a step in G. But we sort of need to make the whole thing undirected and stuff. So you have to add a few more technicalities. So that's why we have to do these last two steps. Because if you thought it through, it'll make it symmetric and you can go back and forth. Okay. All right, so yeah, okay, because you can imagine you have V2 and I4. There's some number that gets from I4 to I3. I3 would take you from V2 to V1 because V1 was the I3's neighbor of V1 and then some other index. Okay, so in other words, these last two steps are in some ways to make sure that, so if I only had these two steps, which is maybe the more intuitive part, take a step in H and use that to take a step in G, that would give me an asymmetric graph. You can go there, not necessarily go back. So these last two steps actually let you reverse the process and ensures the graph is an undirected graph. Okay. You have to think about it a little bit, but okay. So fine. So ultimately the graph is D0 squared regular, where D0 is the degree of H. Okay. We're eventually going to take H to be a constant degree expander. So D0 will be a constant. So, okay, D might be really big, right? A really big degree, I want to drive it down. And I kind of throw in this constant degree expander to sort of semi-simulate choosing random steps in G. So instead of taking a random step in G, I take a random step in my expander, use that to choose a neighbor in G, and then I do a little extra stuff for technical reasons. Okay. And the high level idea is if H is an expander, right, and G is over here, you want to simulate choosing a random neighbor on G, but you don't want to use the full set of bits to actually choose a random neighbor. But if you take a random step in H, because H is an expander, taking random steps in H approaches completely random very fast. So that random step in H is going to be kind of like taking helping you choose a completely random neighbor in G. The high level idea. Okay. All right, so it's a little exotic. I don't know if there's a better name for it than zigzag. Zigzag is a fun name, but I feel like it also throws you in a loop. Okay. Any questions? Okay, the information will be on the right-hand side, so you can continue to uh, keep track of the info. Okay, so this is what we're going to work hard to prove. So I'm just stating it right away. It's not as easy as powering. So the degree we already mentioned is d0 squared. The number of vertices goes from n to nd because you're taking the product of your original n vertices with a graph with d vertices. And now this is the really tough part to prove, is that the spectral gap goes from the spectral gap of G to the spectral gap of G times the spectral gap of H squared. At a high level, it's kind of like you're taking one random step in G and two random steps in H, and that's kind of going on, but anyway. All right, but if H is an expander, let's say gamma H is really big, like 3/4 or 9/10 or something, then gamma G is only going to go down by a constant. Right? If gamma H is a constant, then gamma H squared is a constant. So you go from gamma G to gamma G divided by 1.01 or something. Okay. And so you're hoping that, especially if gamma H is a very good expander, then you're not losing too much. Okay. The win is that the degree is now under control. Okay. All right, let's see what's coming up. Okay, so, all right, so the algorithm is going to ultimately alternate between powering and the zigzag product. Powering, zigzag product. Powering, zigzag product. Improve the spectral gap, bring down the degree. Improve the spectral gap, bring down the degree. And we want to show that overall, the spectral gap still improves. Okay. So, so actually, we're not even going to do a very fancy power. We're just going to do G squared. Okay. So, okay, I left these blank for you guys just to make sure we're on the same page. So the zigzag product of G squared and H. So I take G, I square it, and then I do this crazy thing with H. H has degree D0. Okay, how many vertices is in this composition? ND. Good. What is the degree? Sorry? Oh, there's actually no K. We're just doing G squared. D naught squared. So initially the degree does go up from D to D squared, which is bad, but the zigzag product just brings it back down to D0 no matter what the degree was. So that's how we end up with D0 squared. And then finally the spectral gap is not quite. It will include ZGH, but it's not just ZGH. Where are my notes? Seriously. What would the spectral gap be? Yeah, we just multiplied the two things together, except K is plugged in for 2, I think. Okay, so 1 minus gamma squared. This is coming from initially taking the product and then gamma H squared. Okay, I guess this could be simplified. because 1 minus gamma g squared is something like 2 gamma g minus gamma g squared times gamma h squared. Did I do that right? Okay, so even if we stare at this, think of this being a very high constant. And in the worst case, we're worried about gamma g being super small, right? Like 1 over n or something initially, and in general smaller than any particular constant. So multiplying by 2 is a huge win. Makes the spectral gap twice as big. We lose a little bit gamma g squared, but gamma g is already so small. Gamma g squared is nothing compared to 2 times gamma g. And then, okay, there's a factor of 2 we lose here. And then as long as gamma h squared is something bigger than 1/2, then we should make some progress overall. Okay. So I guess that's why I chose these numbers. 2 gamma g minus gamma g squared times gamma h squared. Okay. So I guess if I plugged in gamma g is at most 1 over 16 and gamma h squared is at least 3/4. I hope this works out. All right, what's 2 minus 1 over 16? Okay, 31 over 16 times 3/4 squared. Okay, so we get 93 times gamma g divided by 16 times 16. I feel like I didn't choose a small enough number. Oh, yeah, okay, good. Save me. Okay, the numerator should be 273. Denominator should be 256. Feel like I should have known that as a computer scientist. Okay, but we've made progress. Yeah. Oh, 279. All right. 1 point for Gryffindor. Okay, but the point is that this is bigger than 1. Okay, and we've made constant progress on gamma g as long as gamma g is small enough. Okay, and once gamma g is at least 1 over 16, we're just done anyway. That's good enough to de-randomize everything. Okay, so we can make progress somehow by combining these operations. Something magical has happened. We played some silly games with these graphs, and we've improved the spectral gap without hurting the degree. The degree is completely under control, and the spectral gap has improved. Right? Okay, something magical happened. Okay. All right. So let's address some of the space components, right? So to be able to actually, you imagine doing this zigzag product combined with g squared several times, right? And so, but you never actually build the graph out explicitly because that would take up too much space. So I need to be able to sort of pretend to be able to do a random walk on the final graph without actually building it. So to do that, I just need to be able to answer questions like, oh, given a vertex, what's the 10th neighbor? Something like that. And if I can answer that question well, that's all I really need to do a random walk. Right? So, okay, so let's look, for example, at g squared. How much space do I need to answer a question like, what is the I1, I2th neighbor in g squared? So I wrote it as 2 indices because, g squared, you take 2 steps, right? So it should be, the degree is d squared for some d. So that's how I broke it down. Okay. All right. So if you want to, answer this question, it's not really so sophisticated, right? Say, okay, you would query the ith neighbor, I1th neighbor of V in G. So, we should imagine this kind of being done recursively. So G squared might be very high up on your stack. So you just go down and say, hey, what's the ith neighbor down here? Something recursively happens, right? And then that gives you some vertex u, right? And then you can query the I-tooth neighbor of u in G. That gives you some w, and you return w, right? So the total space is basically constant plus the recursive calls. Okay, because it's space, not time. I guess maybe what I should really write is you probably need to write down the name of u or something. So maybe it should be max of log n. Something like that. Okay. All right, but you really need to do very little beyond the recursive part. The squaring adds nothing. All right. And so, okay, what about for the zigzag product? Again, each edge is sort of named by two indices k1 and k2 corresponding to the degree in the smaller graph h. And we do something similar, right? Okay, I need to take a step from h from I1 to I2, so I just do that step. I mean, h is small enough to just keep in memory, so it's not a... h is only going to be... okay, so then... oh, right. Okay. So for us, d0 is a very small constant, and then d squared is like coming from d0 from a previous iteration. So d squared is a modestly larger constant, and then we always kind of keep it between a small constant and sort of a big constant. So h itself is just constant space. It's some polynomial in d. So you can keep all of h in memory in constant space. Okay. And so, okay, you can figure out how to do a step in h in just that constant space. Then you have to figure out, then you have to do a recursive call to G to figure out, oh, what's the I1th neighbor of your vertex in G. And then you have to figure out like the I3 part, so you have to do the reverse, but that's just a bunch of subcalls again to the previous graph. And then you take another step in H. Okay. So again, you're really just doing constant memory plus stuff from the recursive calls. Okay. All right, so all put together, okay, so all put together, you basically have some constant times the depth of the calls, right? So if you did this zigzag product G squared thing k times, it should be big O of k space. Okay. All right. How big will we take k to be? So how many times do I have to do this combination of G squared and zigzag to go to a constant expansion? I should mention that originally the original graph has always 1 over poly n expansion. You can do a lower bound. So the minimum spectral gap was always a polynomially small n. How many times do we need to do our thing to get it up to some constant like 1 over 100? The constant's not going to be enough. Log n. We were making geometric progress. Every time it's going up by 1.01 or something, right? How many times do you go up by 1.01 to go from 1 to n? It's log n. Okay, just like doubling. Partly because you only need to multiply by 1.01 a constant number of times to multiply by a factor of 2. And then you just log 2 of n. Okay, so k is log n. That's how many times you have to take this zigzag thingy. So the depth is k, which is log n, and you end up needing log n space. You could be a little bit more careful writing out the algorithmic details, but I think you guys get the idea. All right. Okay, all right, so the algorithm kind of makes sense. at least like what the algorithm's doing. There's something magical going on in how the zigzag product works and why it's able to pull off these bounds that we'll do next. The high level idea of the algorithms to somehow compose graph powering with the zigzag product and then just ramp up the spectral. Yeah. I mean, I don't think anyone's coding or actually implementing this, but okay, but it's pretty spectacular. Okay. All right. So, okay. All right. So, okay. So it seems like the magic is happening in this zigzag product. So for the rest of the class, we're going to try to analyze this thing. And I guess I'm going to try to do it from the back of my head. So we'll see how it goes. Maybe it's good for me to do it this way. All right, so let's let R sub H denote the random walk on H. Okay. Actually, R sub G is almost never going to show up because we're actually never doing a random walk on G anymore, interestingly, right? Because now we're only doing basically random walks on these various H's and then using this zigzag thingy to coordinate steps in G. Okay. So I can write, one of these complicated multi-part steps as this thing, I tensor RH. I'll explain why the tensor notation shows up. But for the moment, we'll just let this denote, just that thing that, I'm on a vertex in G, I'm on a vertex in H, and I just take a random step in H and I stay where I am in G. So I think of I as sort of the identity on the G side and R sub H as a random step on the H side. Okay. And then Z is the thing going on in the middle where I'm looking at where I am in H, taking a step in G, and then looking at where I came from in G to take a step in H. Okay, so those middle two steps, the B and C, I'm wrapping that up in Z. Okay, it's just some matrix describing this step. It's actually deterministic. Okay, so I mean, it's like a random walk matrix, like all the things will sum to one and stuff like that, but there's not much randomness. It's just a 1-0 matrix. Okay, so I can write our funky thing as the composition of three things: random step in H, this deterministic zigzag step, and a random step in H. Right? Okay, I'm just setting up notation here. Now, contrast that to the following. So suppose that was supposed to be erased, but it's not. I guess that's okay. All right. So let's let S denote not a random step in H, but like randomly sampling any vertex in H. Okay, so that's just like the all ones matrix normalized by D. D is the number of vertices in H. Okay, so S is just going to take your standing at some vertex in H, and S will send you anywhere in H uniformly at random, as if the graph was a complete graph with self loops. Okay, and instead look at this. So imagine I replaced the random step in H with a completely random vertex in H. Okay, so what each step would do is I would be at a vertex in G, at a vertex in H. I would sample a random vertex in H, and I would use that to choose a vertex in G, and then that would also force me to move in H. But then I would randomly sample another vertex in H. Okay, so if you put that all together, then I'm really just taking a random step in G, and then picking any random vertex in H. Why? Because G has D choices, right, in a step. And on the H side, I'm just choosing any vertex randomly in H, so that corresponds to any choice on the G side. Okay, so, and then at the end, I randomly sample another vertex in G. So this is written slightly wrong, but this really corresponds to taking a random step in G and a uniformly random sample in H at the end of it. All right. But that really means, how fast does the random walk mix, right? What's the spectral gap? On the H side, you're just always at the stationary distribution. It's always uniformly random. So you're really just completely bound by the G side. So really, you're going to get the same spectral gap intuitively. We'll do it more slowly analytically, but you're really going to get the same spectral gap as G on S because you're really just doing a random walk in S. Random walk in G. I think I'm just randomly mixing G's and S's, but I think you guys kind of understand. Okay. All right. All right. So why? Okay. So here's the high level intuition of the analysis that we're going to do. Okay. So we have these two different things. Intuitively, if H is an expander graph, roughly by definition, a random step looks a lot like sampling a random vertex. Why? Okay. If you take log n steps, you're the stationary distribution, but it's a constant degree expander, so the stationary distribution is uniform. Okay. So in an expander, you need log n steps, and a uniformly sample, you only need one step. Okay, but that's a relatively small difference is what I'm suggesting. And that a random step in H, especially iterated over and over again, is going to behave a lot like a uniformly sampled vertex from H. Okay? Even though you only have d0 degrees of freedom. So in other words, we have this graph H that, for example, would have been very easy for deterministic connectivity. Random walks mix really fast. And we're sort of using it as a gadget to sort of ramp up the G side. To kind of amplify and make G better behaved. So that's what we're going to try to show, is that at some level, the original thing we're analyzing is behaving a lot like a completely random walk in G, and that would have the same spectral gap as gamma G. Then we wouldn't lose anything on the spectral gap. We will lose a little bit. As we saw, you'll lose some gamma H squared. Okay, but that's the intuition. Okay, so how do we articulate this? Is this worth? No, I didn't even. Okay. All right, so we need a little bit of preliminaries. I'll end up putting everything on the right-hand side, so you don't have to memorize it. Okay, so just like you have outer products and tensor products for vectors, you can have tensor products of matrices, and actually it's behaving in the exact same way. It's one reason why I prefer this notation of the outer product. Okay, so if you're given some A and B, where A is an m by n matrix, and B is an n by n matrix, okay, then A times B becomes a linear map on R m by n, defined like this. Okay. Okay. That special case is just one way to help understand what's going on. Here's maybe an important fact. A times B, or A tensor B, if A and B are symmetric and they have stuff, the eigenvalues of A tensor B are going to be lambda A, lambda B, where lambda A is some eigenvalue of A and lambda B is some eigenvalue of B. Okay, that sort of follows from here, because if you have some eigenvector, so if C is an eigenvector of A and D is an eigenvector of B, then AC will become lambda A C, BD will become lambda B. Okay, so C tensor D would be an eigenvector for this A tensor B. Okay. All right. So fine. So there's just it's really what it's like lifting dimensions. It takes a little while to get used to, but we just need to know a few algebraic identities to get us through this proof. Okay. And for us, actually, it's a little bit simpler because one side of the tensor is always the identity most of the time. So if you wanted to plug in, for example, okay, so the identity tensor RH, that's something we'll be studying. It's going to be a linear map on RV times D. That means it takes input something from RV times D. It outputs something in RV times D. So the full dimensions of it, if you wrote it out as a matrix, would be like RV times D times V times D. Okay, but don't have to think about it that way because it makes your head hurt. But if you give me some X in RV times D, you can think of that as a matrix. And I apply I tensor RH to it, and I look at I guess the vth row. So it's taking as input a matrix, it's outputting a matrix. If I look at the vth row, it'll be taking a random step on the vth row of X. Yeah, whatever. Okay, this identity also follows. Fine. I realize it's a little bit exotic, a little bit unusual. So we'll just have it on the right hand side so you can just pattern match when we need to use it. Okay. All right. Okay. All right. Let's do some analysis we're more comfortable with. All right. So we can apply the spectral theorem type of stuff, and this is not 100% accurate because it's really similar to this. The normalized matrix will break down, but roughly we should be able to write RH as the outer product of orthonormal vectors. And I'm missing some d to the 1/2, negative d to the negative 1/2 on the outside, but it doesn't really matter. Okay, so RH is equal to V1 outer product V1 down to the end with the eigenvalues. The first eigenvalue is 1, so that's just left there, right? Okay, now I know that that the first eigenvector is 1s, right? So, I mean, we're really analyzing the normalized thing, but that's okay. Okay, so what does that tell me? That means that V1 should be proportional to the all ones vector. Okay, and there's D entries because we're working in H, so that's 1s over square root D. The first term will look like 1's outer product 1s over D. So that's the all ones matrix except divided by D, so that everything adds up to 1 along the rows and columns. Okay, fine. Okay, so let's, in particular, that was also equal to our matrix X from this before. So we can write RH as, S plus, and the rest of the stuff. Okay. All right. So, okay, if we look at, if I subtract out gamma H parts of S, where gamma H was a spectral gap, right? It's the difference between 1 and mu2. Then what's left has all its eigenvalues in this range. Because I'm just subtracting out a little bit from that first component, and everything else was already in this range, and okay, so that's fine. All right. Okay, so this step is not super exciting, but we're just going to plug in, this RH is equal to one thing minus the other, and then we'll have to break it out into terms. Okay, so this is RH minus gamma H S Z I outer product RH minus gamma H S. Okay, and we're going to factor this out into the corresponding terms. So keep in mind that we can use this identity down at the bottom where the A plus B can just be broken up. So we'll break up all the minuses, which will be pain. Okay, so hopefully I don't forget any terms. Oh, sorry, let me write it differently. There should be RH prime plus. RH prime plus. Thank you. Okay. Don't call me out, but then when I do correct it, everyone nods. So I think you guys know. Okay. All right. So it's very kind of you. All right. So let's see. I'll do it this way. I want to put the S's first. So we'll do gamma H squared So you can also pull out scalars, I outer product S. That's one term. Another term is gamma I, oh, I have to write out the full thing. Okay, Z I outer product S. Another one would look like gamma H I outer product S Z I outer product R prime H. I think you guys get the idea of what I'm doing. It's nothing sophisticated. This will be the other one with the terms flipped around. It's kind of silly because the next slide has this all set up. I guess we should do it once. Okay. But all I'm doing here is factoring. Okay. All right. Because we're going to try to analyze the spectral gap. Okay. So this should be all the terms. Okay. All right. So at some level, I know that the okay. All right. So okay. So what I kind of want to do is I want to analyze these parts separately, and I want to understand their eigenvalues, right? Because I want to show that the whole eigenvalue of the composition is nice and good. All right. So to do that, we need a little bit of notation. I don't know if we've done this before, or you might have seen it before. So just like other norms, Euclidean norms, etc., you can define norms over matrices. So a common one is called the operator norm. Okay. So the operator norm of A is, okay, what's the maximum magnitude of AX over all unit vectors X? Okay. In particular, if A is symmetric, right? Maximizing AX was actually how we got the first eigenvector. Okay. Although this is going to take the absolute value, so it's really the maximum absolute value of any eigenvalue. Okay. And it's not hard to plug in, if you want to maximize A plus BX, okay, that's at most, choosing the best possible X for A and the best possible X for B. So you get a norm of A plus B is less than the norm of A, norm of B. Just like here, you want to kind of plug in the best X here, but it's sort of like, okay, well, I could try to first plug in the best X for B and multiply it times the best X for A instead of just restricting myself to the output of B. So you get this inequality. And because the eigenvalues of the tensor product are multiplying the eigenvalues of the two matrices, we also get this. Okay. I guess it might actually be equals, but all right. Okay, so whatever. This is very convenient because we can start kind of playing with these matrices almost as if they're vectors, right? We can start manipulating them geometrically. That makes life easier. Okay, so all right, this is where I wish I had some notes. Let's look at this term. Okay. All right, so this is at most okay, so we can break this up, right? Okay. So we just need loose upper bounds. What is this upper bounded by? So this describes a random walk on H and stay in the same spot in G. Okay. But really the eigenvalues of this will correspond to the eigenvalues of I, that's just one, times the eigenvalues of the this completely uniform sample. But this completely uniform sample really only has one eigenvalue of value 1, which is the corresponding to eigenvector all ones, and everything else is 0. This is actually equal to 1. But in case it's a random walk, so it's always at most one. Okay. This also describes some kind of random walk kind of thing. It's a deterministic thing, but whatever. You start at one vertex, you end at one vertex. So this will also be bounded above by 1. Okay. Now this, we can do a little bit better than 1. Why? Maybe I can scroll down a little. Yeah, okay. So in general, this is at most I r prime h, right? And then the whole point of r prime h is that it has a smaller thing. Okay, so this is at most 1 minus gamma h. Okay, so with that, we can start annotating all these things. So this is at most 1 minus gamma h. Oh, but there is also a gamma h in front. So that whole row is gamma h 1 minus gamma h. And then this thing is also going to be gamma h 1 minus gamma h. And then this would be, okay, good. Oops, that's an alpha. Okay. So if I add all these things up, I think you would get 1, and it looks like a negative 2 gamma h is canceled by 2 gamma h up there. And then you get minus gamma h squared. Did I add that up correctly? Okay, fine. Okay. All right, so all that's left is this first term. So all of this is at most 1 minus gamma h squared. All right. Now I'm actually really interested in the eigengap. Okay. And actually I know that it's still a constant degree gap. So I actually know that the eigenvector, the stationary distribution is going to correspond to the all ones vector. Because the zigzag product graph overall will still be a regular graph, and the stationary distribution is proportional to the degrees. Okay. So, okay. So in other words, I want to figure out sort of what's the second eigenvalue of this thing, something that's orthogonal to the, okay. Let's try to understand the eigenvectors and eigenvalues of this. So this again was sort of our simplified zigzag product. Sample a completely random vertex in H, take that step in G, and then sample another vertex in H, which was, as we pointed out, at the end of the day, is the same as taking a random step in G and sampling something random in H. Okay. So this should be R sub G. Okay, so the eigenvalues of RG outer product S should be the eigenvalues of RG times the eigenvalues of S. The eigenvalues of S is just ones and everything else is 0. So you're just left with the eigenvalues of RG as far as the non-zero ones go. So that's 1, mu2, mu3, mu4, down to mu n. Okay. So the first eigenvector will be 1, and the rest will be at most 1 minus gamma 2. Or 1 minus the spectral gap, sorry. Okay. So, at some level, if I want to understand the spectral gap of the whole thing, right, then if I look at any x as orthogonal to the all ones vector, because that's the stationary distribution, okay, then what do I know? So all of this part will be at most 1 minus gamma h squared, because that's what we bounded all those operator norms to be. Okay, and this will be gamma h squared gamma g 1 minus gamma g times okay, this kind of thing. Okay, this is coming from taking the operator norm of everything. Well, taking the operator norm down here, and down here, just keeping in mind that it's orthogonal to the all ones vector, and so you're left with 1 minus gamma g. That's either mu2 or negative mu n. Okay, so we add that all up, and we get gamma h squared minus gamma g gamma h squared plus 1 minus gamma h squared, which is 1 minus gamma g gamma h squared. Will bound any second eigenvalue. Okay, which implies that the spectral gap is 1 minus this thing, which will give you gamma g gamma h squared. Okay, all right, that's it. That's the whole proof. I'll clean up the typed up notes so that it'll make some mild sense. But yeah, this is one of the cooler things that we do in this class. I know it's a little, I'm not expecting you guys to be able to regurgitate the whole proof on the exam or something like that, right? This is more just like, okay, this is kind of the outer reaches of randomized algorithms, some of the cool things we can do, right? Okay, all right, thank you.